Hi, everyone. Thank you so much for being here. My name is Angel Kamari. I work in the Office of Communications. We're going to kick off today's event, our 10th Beating the Odds event here at Goddard, with hearing from the founder, Rocco Scalzi. Rocco, if you can join us.
Test 1, 2.
Thank you, Travis.
You got it.
I promised Travis and Angel that I would be short, but now we have a little bit more time,
Have
right?
more time.
Okay.
Take your time.
But we have our special guest that has to be leaving us around 1:30, right, Scooter? So we're going to do some neat things before you leave, okay? Again, welcome everybody. I want to thank all the students. I want to thank all the teachers, parents, for working with the Beating the Odds Foundation, the principals and superintendents of the schools that see the value in this program coming together with the students. I'm just going to give you a real quick, brief intro, background on Beating the Odds, the foundation that I started 35 years ago when I brought 15,000 students to Pittsburgh, to the home of the Pittsburgh Steelers, and we kicked off this message of hope, okay? Never quit, never give up. Now, you guys today were here to learn about NASA and about its work. Who knows? One of you may be an astrophysicist, right? Or an astronaut, or an engineer, which has happened in our program, right, Teresa? We had one individual that became an astro engineer for the industry. Okay. And maybe one of you sitting out of there will become an astronaut. Who knows? But other than becoming an astronaut or astrophysicist, the big message behind Beating the Odds, why I started it all those years ago, I had to beat the odds, okay? Unfortunately, as a police officer, not too far from here in the city of Altoona, and we can see Altoona's here, okay? I had to make a split-second decision during a hostage situation to turn my world upside down. In that split second, fearing for my life, when an individual was turning a shotgun on me, as I jumped through a door into the dark, an individual lunged through that door. I thought I was going to die. Split-second decision. I had to do what I had to do. My bullet struck one of the hostages by mistake. Turned my world upside down. 3 years after the shooting, I had serious problems, drinking problems. My marriage was about over. And one night I ended up in a program up in Boston for burned out police officers. So I did a TV special with Geraldo Rivera. It was called Cop Killers and Killer Cops. It was during that time I was asked if I'd be willing to come into some high schools and talk to high school students about my story. First I said no. I really didn't want to stand in front of high school students and share the story of a shooting. But the more I thought about it, I remember when I was your age, when actually younger, when I was only in about the 5th or 6th grade, our school in Altoona went on an all-school assembly program out of Mansion Park, put on by the Pennsylvania State Police. And as a 10, 11, 12-year-old kid sitting there watching them on horseback, motorcycles, shooting balloons out of the sky, I went home that day and I said to my parents, I know what I'm going to do. Someday I'm going to become a police officer. That became my dream, became my goal. So I did go to that school and I did speak to those students. Little did I know I would receive hundreds of letters from students telling me their stories. And as I read those stories, I realized, wow, we got a lot of issues. And I knew that from being a policeman on the streets. So, a few years later, after going into many of these schools, meeting many of the students and the teachers, seeing the need, we decided to do an event. Instead of going to all these schools separately, let's bring everybody together. And little did I know, one day we would be standing in front of 15,000 students to share our stories. And that's when I started the program Quarterbacks, the quarterbacks of life. Using a football analogy, the quarterback on the football field is in charge of taking the team down the field against the opposition into the end zone, score points, win football games. Quarterbacks of life. That's all of us. We may never play football as a quarterback on the field, but we all can be the quarterback of our lives. What do you want to do? What do you want to be? What do you want to have and give in life, okay? And that's what I began to push. So little did I know when I knocked on the door of a great football player from Pittsburgh, a United States Army veteran, hero during the Vietnam War, lost part of his foot, his thigh, told never, ever be able to play football in the National Football League. He refused to listen. He beat those odds. He played 11 years with the Pittsburgh Steelers, winning 4 Super Bowl champions. The second person I went to join me was Bob Whelan, another Army veteran, Vietnam War. Bob was a great athlete growing up in school, drafted by the Army. Before he was able to sign a contract with the Philadelphia Phillies as a pitcher, sent to Vietnam. Stepped on a booby trap in the ground, blew him in half instantly, pronounced dead, put him in a body bag, onto a helicopter, and back to the base. But he didn't die. They felt a pulse beat. They unzipped him from the bag, pulled him out, saved his life. Bob went on to inspire the world with his walk across America on his arms. Took him 3 years, 8 months, and 6 days to achieve that goal. That's when I realized stories are powerful. Stories can help you beat those odds. And that's what we do. We continually look for those quarterback life stories. We have today with us 2 special guests. You met some of them when we were walking around here. Scooter Altman, okay, astronaut, great individual, left for reasons not left. The Air Force, because he'll tell you that, why, okay, and became a fighter pilot, United States Navy. I'm Navy, so we connected. Great story. You know, he's here to spend a little bit of time with you. Maybe we can do a Q&A. And Charity, you know, we just met not that long ago, recently. Incredible astrophysicist, incredible person, incredible story. Her story melts your heart, breaks your heart, okay? And we can get into that down the road in the schools and do some things that we're talking about doing, okay? So that's the story. That's the game plan. That's why we're here today, to help you guys beat the odds. And there's so many other people, you know, that our sponsors up here, at least they were up there, all the people that get behind what we do, okay? So at this time, you guys are quiet. Are you guys nervous for getting up here? No. You guys will be fine, okay? Take your time, think of what you're saying, speak loud, okay? And own it, feel good about it, okay? You guys will do great. Okay, at this point, Scooter, come on up. Charity, come on. I'll get you guys in a second.
Okay.
Why don't we do this? Why don't we have you guys talk, questions, okay, for our 2 guests. Come up with some questions that you would love to hear some answers to, okay? Make sense? Everybody good? Okay, who's going to be starting it off? Here we go.
How was the journey to become an astronaut? Well, that's one of the things I wanted to talk about is because I remember sitting in chairs like you all are doing, wondering what was next, and I had a plan. I wanted to be a pilot. I thought going to the Air Force Academy was the best way to become a pilot, and everything. I got an appointment to the Air Force Academy. I played basketball in high school. I was trying to do everything I thought I could. When I told my parents when I was 3 years old I wanted to be a pilot, they said, you know, Scott, you can do anything you want as long as you remember 3 things. Work hard, always do your best, and never give up on your dreams. So here I am. I'm a high school junior. I think my dreams are about to come true with an appointment to the Air Force Academy until I take the pre-induction physical, and I'm healthy, I'm in good shape, but my sitting height, they said, Altman, you're too tall to be a pilot in the Air Force. And just like that, my dreams seemed to crumble. But the thing I think that's important to remember is not when somebody tells you no, it's what do you do after that. So I went to college, studied engineering, and I found out that the Navy had a different program, and I could become a Navy pilot even at my sitting height and that opened the doors for me. And then because I had an engineering degree, it opened the door for test pilot school, which then opened the door for the astronaut. And but that didn't happen in a straight line either. It was a complicated road. So I interviewed, went home, and when I got the call, they said, no, we don't want you. So I had to, I was still in the Navy, I went back to sea, got a call for an interview, and then the second time around, they said yes, and I became an astronaut and flew 4 times. So that's how I made it to become a NASA astronaut.
Thank you, sir. Questions? Come on, guys. Yeah, ladies.
How do you think becoming a quarterback for life would actually change the impact that we're trying to make?
Me? Because of these assembly programs, you know, I would visit, how many schools here and here have I visited? I know quite a few of you guys. When I come into your schools and we do assembly programs, your teacher, Mr. Hatch, right, you remember when he was a student, sitting in the auditorium, your brother, and watching the program, right? And I saw you not that long ago on the street, and I remember you saying to me the impact that program had on you. That's how we continue to do what we do, because we see it in you. We see that passion. You guys are young. Just think of all what you can do from now until you get to be my age, which is old, okay? So you guys have the whole future ahead of you. If you work hard, as Scooter said, never give up. You know, keep focused on what you're doing. Have that game plan in front of you. You know, you can achieve it. You can become. And the important thing is get excited about what you want to do. If there's not excitement there, think about it more, okay? You want to be excited about what you do. When I said I wanted to be a cop, every day I couldn't wait. Graduated, I see cops on the street. I talk to them as a kid. They tell me what to do. I played sports in school. Graduated, went to the military. Came out, went to school, got a degree in criminology, became a police officer. It was a big journey, okay? But you guys are young. You can get there, okay? Thanks for the question. How about for Ms. Charity? Any?
So one of the things that our kids focused on was really looking at success stoppers. Like, what do you feel like was one of your biggest success stoppers, and how did you overcome it?
Yeah, well, actually, when I was about the age of everyone in this room, I asked one of my teachers what I could do to work for NASA one day, because I had no idea all the jobs that there are here, and he actually laughed at me, and that really affected me. But looking back, you know, for him, he just saw my life for what it was. Neither of my parents graduated high school. I grew up in this tiny little town. Nobody around us was scientists or engineers. And so I just didn't know that path I had never seen before. And so the first time I went to school, I actually became a registered nurse, because that was something that people in my town could do. And it was a way to get quickly out of poverty. But then as I was working as a registered nurse, the emotional toll was really heavy on me. And I started reading books by popular science, you know, authors such as Carl Sagan and Stephen Hawking, and that really inspired me to go back to school. Again, it was the passion for astrophysics that I decided to go back to school for it, and that's when I learned that there's so many jobs here at NASA. I work here at NASA now, so if anyone ever laughs at you for your dreams, just know that that's a limitation on their own mind. They just don't have the imagination, and don't let that ever stop you.
Thank you.
Yes. Good question.
Well, hopefully some of you in the audience have seen the original Top Gun. Is that true? Put your hands up if you have. Do you remember the scene in the movie where Tom Cruise goes inverted over the, I'll just call it enemy airplane? We don't really know what country they're supposed to be. But that was my scene. So when you watch that, I will tell you, that's my finger in the movie. And yes, we did meet the actors. We flew them in the back seat of the airplane for about a week while we were making the movie, until the director came to me and said, you know, Scooter, we can't use any of these scenes in the movie. I'm like, why not? Are we not doing a good job? And he said, no, you're hitting the marks, you're doing the right moves. But when I look at the dailies, the actors all look kind of green. And Tom Cruise did fill his air sickness bag in my back seat. But he was so excited about flying that then he became a pilot after that. He took flight instructions, and now he owns a P-51 that he flew in the new movie, and I don't. So
Thank you so much. Thank you, Rocco. Thank you, Scott. Thank you, Charity. We're going to move on to the next section.
Oh, we're good? Okay. Thanks, everybody.
Thank you so much. And now we're going to have Travis Wohlrab, Public Engagement Specialist here at Goddard, to give us the NASA Goddard keynote presentation, followed by a Q&A.
All right. I'm good, thanks. All right, tough act to follow, am I right? Here we go. All right. Well, welcome everybody. I hope you enjoyed your tour this morning. I know I was with a couple groups there, Hollidaysburg, Lower Highlands, whoop, right? What's up? Okay. For the rest of you, my name is Travis Wohlrab. I work here as a public engagement officer, specialist, I don't know. These titles don't really mean much. What my job does do, or what I do is I inform the public about some of the science that we do here at NASA Goddard. And it's not just science, we do a lot of engineering too. And you saw examples of that throughout the day today. One of our 4 core science areas that we were not able to see today is heliophysics, which is the study of the sun. So I'm going to start with that. But before that, I just want to say that I'm standing before you today against some significant odds. You might say I beat the odds to be here today. I was estranged from my father since birth, so raised by a single mother in a very modest way north of Chicago. And I also survived a horrific car accident as a passenger in a vehicle when I was 20 years old, when I was in college. So these two things have combined to sort of make me appreciate every single day that I get to walk through these gates. I've always had a dream of working at NASA. Don't think I had the grades to get here, but I definitely took a different route. I joined something called the Peace Corps. If you heard of the Peace Corps, it's also a government agency. And you pretty much volunteer 2 years of your life. You go to a developing country somewhere in the world that needs help, needs technical assistance, and you pretty much integrate with the community, and you're by yourself, and you work on projects and integrate and teach them about America. And then a big part of Peace Corps service is, especially when you get home, is to teach other folks about the country in which you served. Myself, I was in the southern African country called Lesotho. It's very small. Most people hadn't heard of it. I hadn't heard of it when I got invited there. But anyway, look it up. A beautiful culture. Really just one of the most epic scenes that you can imagine up in the mountains in Africa. Anyway, beautiful country, beautiful culture. And so this is where we're at right now. We all got to go inside this building. We're at Goddard Space Flight Center, which was founded in 1959, right? NASA's first Space Field Center, okay? When NASA was founded a year prior, in 1958, there were already some installations such as Langley, which is in Virginia, Langley Research Center. Also, the Jet Propulsion Laboratory had been around for quite some time before NASA incorporated it through a contract with Caltech University. But anyway, this is where it all started. This is where Apollo started. This is where all the network communications with Apollo came through here, and then were routed to Houston. That's still the case today. We have the near space network that is run through NASA Goddard. So you are standing in a very historic place in terms of the space agency, the space race to the moon. And beyond that, you know, our portfolio has continued to grow. And this right here, I think, is a very disorienting and confusing graphic. But I can assure you, what you're seeing on this slide here is an encapsulation of all of the missions that we have and the various parts of science that we do. So, as I mentioned, heliophysics, the study of the sun, is right here. Okay. And so these are all the current active missions or future missions that we have planned. All right, and this is all just to study the sun, which is quite important because if you think about it, without the sun, there would be no Earth. Without the sun, there would be no life. Without the sun, there would be no energy, right, here on planet Earth. So the sun drives everything, not just here on Earth, but in our solar system, which segues nicely to planetary science, okay? So you can see Planetary science is anything in the solar system, and as you heard earlier today, OSIRIS-REx is part of that division, the Planetary Science Division. And that's really just one of the most remarkable engineering feats, to send a tiny spacecraft halfway across the solar system, or at least the inner solar system, to dock with an asteroid and collect some samples and then return it safely back to Earth. I mean, just the sheer amount of logistics and coordination that has to go into that is unbelievable. And now we are reaping the benefits of having those samples here, so we can study them here on Earth in their pristine form, untouched. Those samples are older than the Earth itself. So when you think about that, that's pretty wild, right? We're studying rocks that are older than this actual planet that we live on. Okay? So Earth science, big one. Okay, this is the headquarters for Earth science here at NASA Goddard. And when you think of Earth, it's more of like an organism, right? There's a lot of breathing and interactive parts with our system. We got weather, we have our inner core, we have the oceans, we have wind. All of these things, they come together to create a system of systems. And it's important to understand that if we're to understand how we're possibly affecting it, right? I mean, we know we're affecting it, but to what extent, right? We put these greenhouse gases into the atmosphere. What does that mean for the future? What does that mean for your future, your kids' future, your grandkids' future? Well, we have some very advanced scientific models that are charting a future that are kind of scary, right? And they're going to impact a lot of people that didn't ask for any of this. Talking about shorelines and just extreme weather events. Most of us are just trying to live our lives, right? But the more we pollute the atmosphere, the more we pollute the oceans, we fill it with plastic, the more we're impacting people that are certainly less advantaged. They were going to have to beat some odds themselves just to get by. So we're trying to study that and trying to figure out ways to mitigate that. And that is a core science area here at Goddard. Okay? And then finally, we have the big picture, astrophysics, the universe, right? That's called the area called cosmology, trying to understand the evolution of the universe, okay, where we came from. I'm standing too close to that mic, so I'm going to go stand over here. Sorry about that feedback. But you can see Roman Space Telescope falls into the astrophysics side of things, and many more, okay? We're out there, we're trying to find, we know that there's other Earth planets out there. In fact, there's probably one that looks exactly like Earth, right? With continents and weather systems and weather patterns and lots of water. We want to find it, and we are on the way. We are very close. I'll talk about that in a little bit. Let me show you this chart here, right? Who got to see that eclipse last year? It was just over a year ago. Raise a hand. And even if you didn't see this path of totality, if you were anywhere in the United States, if you put on some glasses, you could see the partial eclipse, right? So this was actually a lot of fun. Got to go to my alma mater, Southern Illinois University, and witness the totality in its full glory, which was awesome because it was right on the center. And I don't know if you remember, the one in 2017 actually came this way, came across the United States, and my university where I went was the intersection. So it was kind of cool to get two eclipses like that. It was a 1 in a billion shot, within 10 years. I like this graph. Somebody made this. This is every total solar eclipse for going from 2000 BC to the year 3000. Okay, so you have 5,000 years of eclipses charted on this model. And you can see, it doesn't matter where you are on Earth, eventually you will see a total solar eclipse go over you, but you might have to wait a couple thousand years. So if you happen to be in that path of totality, consider yourself pretty lucky, okay? Because otherwise you're going to have to travel to go see one. So I don't know. I just thought this is kind of cool to see. This is what math can do, folks. You can figure out stuff in the future, and you can also run things in reverse and see where eclipses have been in the past. And that's what happens when you have very precise mathematical models to talk about that. When you think about that, right, we knew that eclipse was coming down to the very second, okay? And how did we know that? Because there's people that can create mathematical models based on observation, right? So, eclipses provide a good opportunity for us citizens, for scientists, to study parts of the sun that we can't normally see. The sun is very bright, okay? But by a pure mathematical coincidence, the radius of the moon, okay, if you're standing in the right place, will block the entire circumference of the sun, right? And during that time, you can see a total solar eclipse, which is awesome. But what you're able to actually see is the coronosphere, the outer atmosphere of the sun, which is normally blocked out because of the brightness of the sun. So that's kind of cool, right? It gives us an opportunity to study this very dynamic aspect of the sun. You can think of the sun as just being this big ball of fire that sits up there and doesn't do much, but it's incredibly dynamic and very active, and it's very important to understand, and I'll get to that in a second. Here's why. When the sun is at a period of heightened activity, we call it a solar cycle, and every 11 years this cycle restarts. Sometimes we're in solar maximum, sometimes we're in solar minimum, but during maximum, it is burping out a lot of highly charged particles. Now, it doesn't really affect us here on the surface too much, thankfully, because we have a magnetic field around Earth, right, which shields most of us, most of life, from these harmful cosmic rays coming off the sun, these highly charged particles. Now, during a period of solar maximum, that magnetic field is also dynamic, which means it moves, right? It's not just this solid thing, and that can get pushed, right? And if you ever heard of the Northern Lights or the Southern Lights, the Aurora Borealis, perhaps you saw them last summer, maybe earlier this year, especially if you're coming from up north. That was because, normally you can see those in the very northern latitudes, but because the activity was so strong, our magnetic field was pushed, okay? All the way down. You could see Northern Lights all the way down far as south, even south of here. Okay, they were reporting them in Georgia from the one in March, I believe. So here's what it looks like from space, right? Sure, Scooter got to see this at some point as he flew over in the International Space Station, or Space Shuttle. You can see these northern lights on the ionosphere. Okay, this outer film that allows us to live here on Earth, and this is where you have all these interactions between the highly charged particles coming off the sun. All right. Now this right here gives you a good example of what the sun looks like during minimum and during maximum. This is during that 11-year cycle. Okay, during maximum, you can tell the sun. This is where you see the sunspots. All right, you can actually get a pair of binoculars with a solar filter, go out and take a look, and you can see the sunspots on the sun. It's not hard. And those sunspots are those very bright areas that you see on the one on the right there during solar maximum. Okay, and it's during these times that the sun is very active, sending out lots of what we call coronal mass ejections, CMEs. Okay, these can actually be quite dangerous. You get to see northern lights, that's fun, but what it's not cool for is our satellites. Okay, we have satellites that are operating outside of our magnetic field, the magnetosphere, and we also, like I said, when that magnetic field gets pushed, it puts them at risk. Now we're talking about GPS, right? If you're using Google Maps, that could all suddenly go away. But also it sends a lot of electricity into our atmosphere and even our infrastructure. There's been power outages, such as Toronto in 2012, okay? Massive blackouts. There was just one in Spain, and they're taking a look. They don't know what caused that one yet. Massive blackout for 2 days. But they're looking at the solar activity because we are in a period of solar maximum right now. So these blackouts, the sun can actually cause quite a few impacts here on Earth. So we call that space weather. And what we're trying to do here at Goddard and with our partners at NOAA is to be able to predict that, just like we predict the weather, all right? And come up with ways to protect our satellites and our infrastructure here on the ground to make sure that these don't actually impact our systems, okay? So here's what it looks like. Now we have we have a few different instruments, NASA here, we have a few satellites that can monitor this stuff from space. And so you see these big burps, I'll call them burps. They fly out off the sun. And most of the time they're not facing Earth, right? You have to be in the right spot for that to happen, but sometimes we are. We are in this period where the burp will come right at us. And this is what it looks like. All right, you're going to see here, you can see all of these highly charged particles. I don't know why it stopped. It shouldn't have stopped. Anyway, let's move on to what it actually looks like. Let me go back. Hopefully this plays. Bob, you might have to give me a manual start here. There it is. I want to show you this model right there. You see that little burp there? Now just imagine, so first of all, Earth is about the size of a quarter here, okay? That's just the scale between Earth and the sun. But here's what it looks like, all right? And this is based on real data, this model that you're going to see here, all right? This is what it looks like when you have a coronal mass ejection going through the solar system, and we happen to be in the way. At first, you're going to see our sister planet, Venus, which doesn't have the same kind of magnetic field. All right? Poor Venus. Here comes this coronal mass ejection, and Venus is just going to get pummeled by this thing. Okay? Now, it's probably hard to see with the lights and everything, but you can actually see the interactions as it's passing through Venus. You can, oh, thank you. Look at that. Thank you, Bob. You can see right there. You can see the interactions on the surface. It's not good. If you happen to catch one of those in your face, you're going to have cancer and you're going to die pretty quickly. Okay, you're going to get radiation poisoning. But here's the magic of Earth. And our magnetic field, thanks to our iron core, which is spinning, it generates this magnetic field, and you're going to see the coronal mass ejection come by and just get deflected through this invisible force field, right? And so there's a lot of things that go into this as to why this is so beneficial for us. But the main thing is you can see the magnetic field deflecting these highly charged solar particles. Now, again, this field is dynamic, and it can actually, it can get pushed back. It'll never actually go away. It'll get reset at some point. But all this energy coming off the sun drives all sorts of things, such as the wind on our planet. Okay, so here's a model of all the wind. Okay, and this actually, I think these are sea currents, okay? But again, the sun and those particles that are driving it are fueling the processes of our planet that make it dynamic, okay? So you can see here, these are wind, surface wind, and then ocean currents. And they tend to follow a similar pattern, okay? And it's just a beautiful model that kind of shows our connection, right, between the two things. So I know I don't want to talk too much here and miss, but anyway, we have a moon, okay, and the origin of the moon came from a protoplanetary collision way back when, 4 billion years ago probably. And it was a small planet that hit Earth while we were still forming. Most of the material fell back to Earth, but a little piece of it was maintained, the core of that other planet, and spun together, as you're seeing in this simulation, to create the moon, right? And we know that we're pretty sure that this happened because the material you find, the core composition of the moon, is incredibly similar to Earth's, to a very fine degree. So we know that the Earth and the moon were made of the same stuff at some point, and that is probably most likely what happened. And we've run lots of simulations, but that collision is also what put us on a tilt, right? We're on an axis, and this is the reason we have seasons. And the reason why Earth doesn't have this crazy spinning in some oblong, unpredictable rotation is because the moon is tidally locked to us. It keeps us in this 23.5 degree axis, okay? So that's why we have winter, because during those months, we're not getting the direct sunlight because we're on an axis. During the summer, we are getting more direct sunlight because we're facing that part of the sun when we're on the other half. So again, it's all orbital mechanics. It's confusing, but these kind of simulations kind of make it easier to see. By the way, the moon was formed, our latest simulations, that whole process you just saw took about 3 hours, okay? That's how fast that happened. The planet was coming in hot, right? So, let's see what else we got here. The moon. In keeping with the moon, we have really studied the moon. Now this launched, I believe, in 2006, 2009, Lunar Reconnaissance Orbiter. And wow, is it awesome. Probably the coolest thing, I think, is that we were able to finally take pictures of all the stuff we left behind during the Apollo missions, right? There's a lot of naysayers out there, but they're crazy. You can see all these little tracks, right? You can see the lunar module's still there. It's all still there. And it's not going anywhere because the moon doesn't have the same kind of geological features that we do. There's no weather. So you can see the rover tracks from when they were driving around. You can see all the experiments we left. And anyway, it was the first time we were able to directly image that. Even our most powerful telescopes on Earth could not get to that fine degree to image this stuff. We had to put something in orbit that could really zoom in on that. So these are the 6 Apollo missions to the moon, and that stuff is still there, including the flag, which is most likely washed out by now. Apollo 11 and 12, we left something called, well, it was basically a mirror. Okay, it was a mirror experiment. And because of this mirror experiment, what we're able to do is shoot a laser off the moon. We know exactly where this is. Shoot a laser off the moon, wait for that laser to come back, and measure the exact distance, okay, from the point of that laser shooting to the moon and back, right? So because we've been shooting this laser every year since 1969, we actually know that the moon is moving away from us. Now think back to that simulation before where that planet was coming in. Well, that still had velocity, right? Even though the moon is orbiting us and it doesn't seem like it's really going anywhere, it's actually moving further away from us, about 1 to 3 inches a year. Doesn't sound like a lot, right? But when you talk about millions and even billions of years, that could mean trouble for life here on Earth. But what it really means is that we won't have total solar eclipses. In about 250 million years, the moon is going to be too far. And every eclipse that we have will be in what's called an annular eclipse, okay? Where it's just, you'll have to wear glasses to see it, basically. You won't be able to look at it with your naked eye. But because of these mirrors, there's been all sorts of independent verifications. A lot of universities have done this experiment. And anyway, again, the naysayers are crazy. And we have all this evidence. So, studying the Earth, it's a big deal. This is all the, if it plays, there it is. These are all the different satellites, and I took this down yesterday, so you can see this is exactly what it looked like yesterday with our orbits, with our Earth Science spacecraft. And so these are the different spacecraft that are monitoring the Earth in real time. We are collecting over 1 million data points per hour and feeding them into a supercomputer, which informs our models. Okay, and it's not just from satellites, but satellites are actually pretty advantageous because one, they're moving very fast, but we also collect. We have different sensing equipment on commercial aircraft. Okay, so all the flights in the United States are testing atmospheric conditions for us and sending that data back. We obviously have ground stations all around the world collecting atmospheric data, and you know. When you can start to put all this data together, these 1 million data points, you start to get a sense of what's going on here on the planet. And here's a good representation of the different things that we look at. We can see the sea surface temperature and the currents. Okay, this is good. I mean, I bet you all the folks back in the day wish they had that kind of data to know which way the current was going in the water, right? Instead, those navigators had to rely on other methods, and they were geniuses within themselves. They didn't have these tools. Okay, we can monitor the precipitation. We can monitor the soil moisture. We can monitor clouds, obviously. We can, so this is just a handful of the different models that we can create based on all the comprehensive data that these satellites take. Okay, and again, this is very important because it gives us a sense, you know, if we see an extreme weather event somewhere, now we have the data from all these different other measurements to see if maybe they're possibly related. And it turns out that a lot of this stuff is very related. Okay, and this is where you start getting the climate model. You all saw the GPM control room. I don't think that screen was working, so I'm glad that I pulled this down. This is the past 7 days of precipitation around the entire planet. Okay, now when I was living in Lesotho, right here, I wish I knew about this because they didn't have radar there, so I never knew if it was going to rain. But this, you know, you can see right here, here's that atmospheric river that just dumped a bunch of rain along the East Coast past 3 days or so, past 2 days. Let me start it over. It's just kind of cool to see, right? You know, obviously, this is a Mercator projection of the planet, but to see all the precipitation in the world at once, you can see the Sahara Desert never gets any. You can see that a lot of the precipitation that comes off of Central Africa ends up making its way up here, and we're starting to head into hurricane season. You can see why the North Atlantic Current makes it so that the UK, which is up here in the northern latitudes, still has a pretty temperate climate, right? Because the jet stream is going up that way. So again, being able to look at all this in a comprehensive, holistic view is quite valuable for many different reasons. This is just a beautiful model that we have of the sea surface temperature and the currents. Okay, I know it's kind of hard to see, but anyway, you can see how it, you know, as I pointed out before, that precipitation coming off Central Africa gets really warm and strong as it goes up along this current and eventually makes its way to Florida, the eastern seaboard, and the Gulf of Mexico. And you can see right here that this current right here is what spawns off and creates those massive hurricanes that we'll see from time to time in the Gulf of Mexico. Because that water is super hot and it just fuels, right? It fuels that convection, and you get hurricanes like Katrina and Harvey and whatnot. And so being able to understand this is important for forecasting. And also it's important to see how it's changing, right? All of this is changing a lot faster than any of our models would have predicted. So anyway, here's a nice shot of Roman. I know we got to see some of the hardware today, not all of it, not most of it, because it's in testing. But this is what it's going to look like when it's finally put together and sent to space. It's just a beautiful telescope. And it's really going to open our eyes to the universe. And I'm going to show you why. I know you talked about some of this already, but sometimes it's nice to visualize. Okay? We're sending Roman 4 times the distance between the Earth and the Moon. It's going out to a point called L2. All right, here's your sun, and here's L2. Now there's 5 of these L points. Lagrange points are what they're called. And they're around Earth. These are gravitational equilibriums. Okay, so you have the sun and the Earth and Jupiter, you know, somewhere over here, and there's a bunch of gravity wells in our solar system. But this point right here is actually very nice because it's like nothing's really pulling it in one direction or the other. So we like to orbit this invisible point because it doesn't require a whole lot of fuel to stay there. Okay, if you're in low Earth orbit, eventually you need to push yourself back up because there's atmospheric drag, and of course the Earth is constantly pulling stuff down. But out here, it's very, very minimal. So again, that's the reason we're going out to L2. That's where James Webb is. I think one more. But you'll be seeing a lot more spacecraft going out to this invisible point, which was mathematically theorized about 400 years ago by a man named Lagrange. So thank you, Lagrange, for providing us that. I like this picture, and I'll tell you why. This is a real mosaic that the Hubble Space Telescope produced. This is over 600 images, okay, stitched together to create a very detailed view of our nearest galactic neighbor. Anybody know what it's called? Yes, I heard Andromeda. The Andromeda Galaxy is 2.5 million light years away. And yet it's our neighbor. And it's also heading right towards us. Not to fear, though. We've run the simulations. Because there's so much space between the stars, we don't see any collisions. There are no stellar collisions. The only things that will collide is this supermassive black hole at the center of the galaxy. Now, Hubble took this picture, like I said, 600 exposures, and I put this video in here. Hopefully, can we turn the sound off? Forgot to take that out. I mean, actually, it's kind of nice, right? But if you get in here, you know, forget about these brighter stars in the foreground. Those are photobombing. Those are stars in the Milky Way. But behind that, right here, We have all these individual, just hundreds of billions of stars in this one image. And it's beautiful. And you can actually see that, Andromeda is a lot like us, okay? We think that the Milky Way looks very much like Andromeda. It's a sister galaxy almost. And then you start to think like, wow, how many galaxies are there out there? And how many stars are in each? Well, this actually gives us the first survey of how many stars are in galaxies that look like ours. And it's somewhere on the order of probably 50 billion to 200 billion stars per galaxy. And then you start to wonder how many galaxies are there in the universe. And this is where it starts getting a little mind-melty, right? Maybe you've seen this image before. It's one of the most important pictures that Hubble ever took. This is called the Hubble Ultra Deep Field. Okay, this picture was taken on a 1 million second exposure, right? So you open up the lens, you collect light for 1 million seconds, and then you close it. They pointed to a piece of the sky. It's like looking through a pinhead at arm's length, okay? That was super dark. We didn't think anything was there. And this is what came back. 10,000 galaxies. Every single point of light in this picture is a galaxy, each with 50 to 200 billion stars, okay? Every single one. Now, they were very surprised, the scientists that took this picture. They said, okay, that's crazy. Let's look at a different part of dark sky, okay? So same thing. Pinhead, arm's length, over here. Same thing, more or less 10,000 galaxies. They did it 6 more times. As you can guess, 10,000 galaxies. So now we have this idea that no matter where we look, we're going to see about 10,000 galaxies. And you can extrapolate that data, which means, assume if it's here, 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 it's everywhere. And if you do the whole sky, you get 2 trillion galaxies. 2 trillion galaxies with 50 to 200 billion stars in each galaxy. Well, now we're talking about some very big numbers. And I can't wrap my head around that. Neither can you. Or you could try. Maybe you can. I don't know. I'm not going to assume. But the way to think about this, to equal the amount of stars in the universe, not galaxies, stars, you'd have to take every single grain of sand on Earth and multiply it by 10, right? So the short answer is there's 10 times more stars in the universe than grains of sand on Earth. Now, keep in mind the Sahara Desert's about the size of the United States of America, and it's all sand, okay? All the beaches, all the coastlines, all the sandbars everywhere. Think about that. Next time you're at the beach, just look at all the sand and just remember that there are that many stars. Now, what's even crazier is that we think that just about every star has at least one planet. We think planets are, solar systems are part of stellar evolution. And now we know that probably most stars have more than one planet, probably like ours with 8 or more or less. Nevertheless, not all stars are the same, of course. But we do think that when stars are forming, that planets are just a natural consequence. Just like how just about all of our planets here in the solar system have moons. So I don't even want to get into moons, okay? Because now we're talking about some super numbers. But you talk to people here, especially the scientists, the ones that work in astrobiology and whatnot, to think that we're the only ones is incredibly naive. And we are getting very close to being able to build the tool that's going to tell us definitively if we are alone, okay? At least in our galaxy. And again, if you start doing all the numbers, you would think that our galaxy is teeming with life, okay? So if you think that life is part of a natural process, just like planets are part of a natural process of star formation, eventually we're going to be able to at least hone in to these planets and see if there's molecular life in the atmosphere, much like we can see at ours. Okay, so this is a sample of Roman's deep field, that little pinhead, right? But instead of 10,000, there's 1 million galaxies. Hubble's taken 2.2 million pictures of the universe, and that's account for 0.01% of the sky. Roman's going to surpass that in 30 days. Okay? So think about that. Because Roman has such a wide field of view, it's going to surpass Hubble's data set in just 30 days. And Hubble's been up since January of 1990, okay? So let that soak in. 35 years versus 30 days, right? Hubble took this amazing picture of the Eagle Nebula called Pillars of Creation. This is what Romans is going to look like, okay? This is a massive nebula region. This is 6 light years tall, where stars are being born, and this is what Romans' field of view is going to look like, right? And the other big thing is exoplanets. Talk about planets. We are very interested in finding Earth-like planets, and Roman is sadly not going to be able to find ones that are small enough to be like Earth, save for a few different methods that we're going to try out. But this is basically how we find most planets right now. We can stare at a star. So in this example, it's like staring at the sun. And when a planet goes across the surface in a transit, it eclipses it, and we can watch that brightness dip down. And the time as well will tell us how big the planet is. Okay, if the bigger the planet, the more this is going to dip down, and the brightness will also, the brightness of the star will also go down. So this is how we detect planets right now, okay? It's not the best method that we think, but given the tools that we have in space, this is what we got, okay? Right now we've cataloged over 5,000 exoplanets, okay? When I was born in '88, that was 0, maybe 1, but it was like a theory at the time. So this is where we're at right now, and when Roman launches, that number is going to be in the millions, okay? Because Roman has different tools on it that's going to allow us to find more planets. But what we're really interested right now is that first part where the planet starts to cross into the star. And I know I got to get off the stage here in a minute. Right here, that little thin atmosphere. When the light goes through that atmosphere, it gives off a very distinct color based on what's in that atmosphere, okay? If there's oxygen, if there's hydrogen, it's going to give off a certain color. And we're going to know because we can analyze that light, all right? And so that's how we detect the absorbed light versus the light that comes out and transmitted to us. It's called a spectrograph. When we put that through, we'll be able to see, hey, that planet looks a lot like Earth. It has the same atmosphere as Earth. Maybe there's plant life on that planet. Maybe there's animals, exotic alien animals. So these are the things that we're building our next generation space telescope after Roman to look at, because this is all new science, right? So maybe someday you'll work here, maybe someday you'll be on what we're calling the Habitable Worlds Observatory, all right? And this is what I'm going to leave you with. The Habitable Worlds Observatory is an ambitious, brand new telescope, and there's a few different designs, right? It's still in the design phase, but it kind of looks like Webb, but it's even bigger. It's going to be looking at all sorts of different kinds of light across the whole electromagnetic spectrum. But the main goal is to be able to image these Earth-like planets. Planets that are so small, yet so important to understanding of whether or not there's life in the universe besides us, okay? We think that we're going to answer that question in the next few decades, all right? So stick around, because I think that, when you think about philosophically, what could be more important than knowing that we're not alone, when you think about that, right? It's a very lonely place, this universe, but being able to detect life through an instrument like this would really be groundbreaking and create all sorts of questions that we would have to answer about our place in the universe. So with that, thank you very much. I don't think I left any time for questions. So. All right, so now we have, yeah, go ahead.
Thank you so much, Travis, for the informative PowerPoint and presentation. Now we're going to have Jennifer Edmundson and Corky Clinton virtually giving us a keynote presentation on NASA Impact mission.
Okay. Let's go. First, we want to start with your definition of success. And of course, the first thing we've got to do on this end is decide what are our dreams and our goals. As you might guess from this picture that we're showing you, our goals are to be able to build structures on the surface of the moon. These structures would be obviously landing pads, which we think will be among the first, if not the very first structures that are needed on the moon or Mars. Blast shields around those landing pads to prevent the ejecta, and there shouldn't be any if we build a good landing pad, but just to prevent anything from flying away and damaging nearby equipment or dwellings or anything else. Roads to keep the dust down and go from one place to another. Foundations that would be needed for any other large structures. Habitats, of course, in the distant future when we can construct actual living quarters for the astronauts and folks living and working on the moon. And then also foundations for power plants. Next chart, please. It might surprise you to learn that we've been working on developing these technologies since 2004. The first time that we actually began a project on this, it was part of the ISFAR program, and that's in situ fabrication and repair. ISFAR was primarily focused on in-space manufacturing, in-space additive manufacturing, but there was an element there called habitat structures. And when we were working in the habitat structures elements, we learned how to combine ordinary Portland cement as a binder with lunar regolith simulant as the aggregate, so we could make a lunar concrete. And we worked with a professor out at the University of Southern California, Professor Baruch Koshnevis, who's still in the business, by the way, on his contour crafting process. And we did learn how to print lunar concrete like I described earlier. Unfortunately, an environmental factor popped up. The president announced the vision for space exploration, and that changed NASA's priorities. With that change in priorities, all of the ISFAR elements were canceled. Moving forward to the early portions of President Obama's administration, he changed the priorities again for the agency and pointed us to Mars. Now, this was a good environmental factor in that it recreated the interest and the conversations about extraterrestrial construction. So we partnered again with Professor Koshnevis and his contour crafting. And this time we also partnered with the U.S. Army Corps of Engineers, because the Corps of Engineers was interested in using this technology on Earth for their forward operating bases. And we shared a common vision, just slightly different between the Corps of Engineers and NASA. The Corps of Engineers' vision was the capability to print custom designed expeditionary structures on demand in the field using locally available materials. Now, our NASA vision was just a slight difference from that. We wanted to develop the capability to print custom designed exploration structures on demand on the extraterrestrial surface using locally available materials. That's a common need. We call ours in situ resources or the regolith that's there on the planet. The Corps of Engineers were just going to use whatever was available in the region. We actually made quite a bit of progress on this project. We learned a great deal, and we used Mars regolith simulant. We actually printed with Mars regolith simulant. We tested those materials, and we learned a great deal about how you print with, in this case, Martian concrete. And the Corps of Engineers learned a great deal about how you print using Earth-based materials for their structures. But again, environmental factors near the end of this project emerged, and I'll let Jennifer tell you about what happened next.
Okay. For environmental factors as well, at the time we had the NASA Centennial Challenge, the 3D printed Mars Habitat Challenge. During phase 1, they had a design challenge where you could design a 3D printed habitat for the Mars surface. After that, we started our phase 2, and that's where I really got involved with the 3D printed habitat challenge. Based on my background in planetary science and some of my experience with the in-space manufacturing team, we were trying to figure out what kind of materials would be beneficial for constructing a habitat on Mars. So we chose materials that could be easily recycled from space station waste. And we also had examples of some of the Martian material, the regolith that we used for that phase 2 as well. And then we had a head-to-head competition in Peoria, Illinois for the phase 3, where AI Space Factory and Penn State University went head-to-head and tried to print a habitat in 2 days. And it was one of the most exciting events that I've ever been to. But that really opened our eyes to differences in construction processes and materials, and kind of created a wealth of just knowledge and a really good base of industry and academia partners, including ICON and Colorado School of Mines, who we work with now. Also at the time, October 2017, Vice President Pence said, "We will return American astronauts to the moon, not only to leave behind footprints and flags, but also to build a foundation that we need to send Americans to Mars and beyond." They put out the Moon to Mars strategy and objectives, and the first one up there is demonstrate advanced manufacturing and autonomous construction capabilities in support of continuous human lunar presence and a robust lunar economy. Perfect for us. Environmental factor. The Moon to Mars strategy and objectives really gave us the authorization, essentially, to go forward. So we created the Moon to Mars Planetary Autonomous Construction Technology Project. Our goal is to develop, deliver, and demonstrate on-demand capabilities to protect astronauts and create infrastructure on the lunar surface via construction of landing pads, habitat, shelters, basically anything that you can think of. We would love to print and just fabricate in any kind of way, any kind of infrastructure element that you could possibly need. And we understand that there's going to be a bunch of different materials and things that are needed, because the materials that you use to build a landing pad, which is what we're targeting in the first place, are not necessarily the materials that you want to build your roads or your habitats or thermal bodies or any other kind of infrastructure element out of. Radiation shielding is another thing, lunar safe haven type development as well. So what we really wanted to do under the project to help in general was develop and demonstrate construction capabilities for in situ resource utilization based materials. And the reason we focused on that was because it's so important to do this economically. We do not want to fly everything that we could possibly need on the lunar surface from Earth because it is so expensive. One of the cost estimates that I saw from one of the commercial lunar payload services lander companies was that it would take $1 million to $1.2 million per kilogram. Now that's 2.2 pounds to get material from Earth to the moon. We have got to use in situ resources. We also have to integrate sensors and process monitoring so that we can make sure that what we make on the lunar surface is exactly what we intended to make, and that we can monitor the structure over time, just in case there's cracks that develop or something that could potentially really be bad for our crew members there. We wanted to test and evaluate materials for candidate processes for use in the lunar environment, and Corky will talk about that in a few slides. And we also wanted to validate the Earth-based regolith simulants, the things that we're using to test our technologies now, and the testing environments that we have, our dirty thermal vacuum chambers, our vibration tests, and all the different things that we do, are sufficient analogs for lunar operations. So we intend to send up a proof of concept demonstration where we will be fabricating something on the lunar surface, test that to make sure that what we wanted to make is exactly what we made. And to do this, we have a variety of teammates. We have so many teammates, so many people are so passionate about this, and I couldn't be happier. We have multiple NASA centers that have contributed to our effort. We have leveraged other government agencies. We got to start our contract with ICON using some of the Air Force contracting mechanisms, and that really has helped us out in the long run. Of course, ICON is our primary partner. They're developing a laser vitreous material transformation process where they essentially laser melt material, and they control the cooling enough that you can get a strong material out of it. Essentially, they're melting all the regolith grains and creating a solid rock out of it. It's really strong. We also have Dr. Holly Shulman. She is working with Radiance Technologies, Ralph Bruce and Associates, Microwave Properties North, they are working on microwave sintering material. Microwaves are really cool because if you've done research into regolith, you know that rocks are incredibly good insulators. They don't transmit heat very well. So microwaves are actually really good at getting energy into the regolith. They actually do transmit the microwaves through the regolith really, really well. So that's a really good energy efficient process for the regolith. So we are also looking at that. We're also looking at things from like Astroport, who's developing essentially a casted brick. BrickBot is what they call it. We're also looking at Outward Technologies in their solar melting. We've been working with different academic partners. Penn State University has looked at geopolymers. Now, that's not mixing polymers or plastics with regolith. That's actually using the regolith and an activator solution, almost like bleach sometimes. You can attack the mineral grains themselves and actually get it to turn into a construction material. It's very, very cool. We've also used the Small Business Innovation Research and Technology Transfer Grants to help build this community. We've been looking at microwave cameras and things like that to give us more information about the regolith. We're also looking at Raman spectroscopy. So hopefully you were able to see some of that at Goddard, some of the different spectroscopy components. I'll go ahead to the next slide, hand it back to Courtney.
So as Jennifer mentioned, from our experience base on the projects that we have been involved with, from our experience base that we gained, excuse me, from the NASA 3D printed Mars Centennial Challenge, and from the experience base that we got when we did a very thorough literature survey about what materials and processes were out there to build on the moon. We evaluated a pretty broad variety of different materials, and we separated those really into two classes. One I'll call cementitious. And for the cementitious, we had binders, like I talked about earlier, the ordinary Portland cement binding with the regular simulant materials. Here we evaluated different binders, but all with the regular simulant. Like Jennifer said, we wanted to make sure that all of these materials would be, excuse me, would be available to us on the moon. And all of the binder materials that you see here would be available in some form or fashion on the moon. However, one drawback to this is that for the larger construction projects, you would have to have an equally large industrial scale processing facility to extract the binder materials from the regolith and then recombine them in the form of a binder that you could use to make the concrete. So that was one of the factors that was working against the cementitious materials. But we're continuing to work, as Jennifer said. When you look at a construction site today, you don't see one material and you don't see one piece of equipment or one tool. It's multiple materials, multiple pieces of equipment, and multiple tools. And that's why we're evaluating a broad spectrum of not only materials, but also processes. So the other type of process that we looked at, we called a thermal process or a direct energy process. And those are the processes that just take the lunar regolith as it is, size sort it, we do filter it, and apply that form of energy to it. Jennifer mentioned the laser that ICON is working to melt the material. ICON is also developing a technology they call molten regolith extrusion. And what they do there is just fill up a cylinder of regolith. They heat it up until it gets hot enough to melt, and then it flows out, and they can almost print with it. The third is Holly Schulman's microwave team. Great team of folks. They're doing an outstanding job. The fourth one, she also mentioned, is being worked by Astroport, and they form tiles. They heat up the regolith material. They form a tile with that, and then they place that on the surface. And that would be a great application for a road, possibly even a landing pad, but we still have some more work to do on that. So those were the two basic types of materials and processes that we evaluated. And we want to show you on the next chart one of those tests that we put these materials through. And while this is going, and we'll let it run several times, we worked with one of the lander providers and worked with them to calculate the heat energy, or what we call heat flux, that the engine exhaust gases from the lander impart to the lunar surface. We have a small test bed here at the Marshall Space Flight Center called the Plasma Torch Test Facility. And so what we do is to get that plasma torch to recreate the heat flux environment that this material would see if a lander were to land on that on the surface of the moon. We actually put a factor of 2 on that heat flux, so this is actually twice the heat flux that the material would see from the lander. And as you can see on the demonstration, and you can see on the left side with the before and after test articles, these materials are going to make great landing pads. Particular material combination that we're showing you here that we tested was produced by Icon's Laser VMX. So great landing pad material, can really withstand the heat flux that any of these landers will put on the surface of the moon. Next chart, Jennifer. Okay, once we went through this evaluation process, which is what we called our down select process, and picked the processes that we would take forward to mature, we had to sit down and come up with detailed plans to make sure that we would meet our objectives. We call that detailed plan a technology maturation plan, or the TMP. The TMP is a series of tasks that are defined with success criteria to advance subsystems to the next level. And those subsystems are the major elements of the final construction system. For our case, the one that we're showing here is the Icon Laser VMX. We have to develop the Laser VMX process and all of the instrumentation that goes with that. We have to develop the end effector subsystem, and that includes the laser once it's finally developed and its process is established. It includes multiple instruments to help us measure the surface temperature and what's going on down there. It includes what we call a scoop tamp filter device that will scoop up the regolith. It will filter it for us. It will lay it back down on a nice smooth layer and prepare the site. Then we have the robot arm that we have to develop with the appropriate software and controls. And then we have the power and the cooling cables that have to be routed down the arm to keep the laser cool in its operational condition. Now, each one of these tasks must be completed, and we review the results of those tasks before we move on to the next task. The particular TMP that you see here, we have completed all but 2 tasks. One, we do have to go back and rerun, and Jennifer will talk about that shortly. Once we complete that, we will be able to integrate all of those subsystems into the construction system and test it in a representative lunar environment. And that's what we call task 30, and that's the big bar on the right-hand side. I'll let Jennifer take it from here.
Okay. We had a GCD redirection, which kind of had us form this technology maturation plan. We also had a schedule put against it, but one of the things about technology development is that it doesn't always work out as you would like it to. Most of the time it doesn't. So there were a few project success showstoppers that we had to identify and mitigate. One is just maybe we chose the wrong material when we had this down select process, and it's come a long way, and we keep testing it, keep making sure. There's some back and forth on the material property. Sometimes we had to switch simulants, we had to switch the geometry of the end effector just to make sure that the process would go as quickly as we were hoping to, because we want to fly this technology, we want to build a landing pad, but we also don't want to spend 60 years on the moon trying to build a landing pad. That would just not work. So we monitor our risks. We basically say, okay, what keeps us up at night? What could we do to possibly control that or mitigate it? How are we going to work out this problem? And we add milestones for this risk management into our integrated master schedule. So every time we keep developing this technology, we keep knocking out those different risks. We also have a resource review and management, a lot of our budget work. We have different contracts with different companies that do different things for us. Like Kratos Southern Research Engineering actually does a lot of our testing. They can give us the thermal properties of the VMX material. They've done coefficient of thermal expansion measurements to make sure that since we're developing this material and it's going to see the extreme thermal swings that you see on the lunar surface, the extreme day-night temperature differences, this material has to stand up to that if it's going to last as a landing pad material. And it has to stand up to the plasma torch as well for that thermal shock property or process. We also have our engineering and project control boards. Basically, we formalize the decisions that we make. We make sure that we have all the background information that we need to make these decisions. We also have frequent and open communications with our teams. We have weekly team meetings where we look over the schedule and we make sure that we have that technical progress, and that if there are any issues, we bring them up. We discuss them openly as a team. We as a team decide, what are the best ways to handle this? What are the mitigation strategies? We also have a weekly leadership team discussion, and that's 3 times a week. And there's plenty of stuff to talk about a lot of the times because there's so much going on. We've got all the toolbox materials we're developing at a lower level, plus ICON's material. There's a lot going on with our team, and it's good to make sure that everybody's on the same page. And that's with Corky, who's our PI, me, who's the PM, and then our chief engineer, Ron Mize. We've got weekly discussions with ICON leadership. If we see any issues or we want to give them a heads up about something, we discuss that in those meetings. And then biweekly discussions with our program executive representative, essentially, who helps us and guides us and also lets the Game Changing Development Program know how things are going with us, and they understand all of the different things we're dealing with, can talk it to them real time. One of the things that we noticed, because we did change the simulants and we did change the end effector configuration, is that some of the material performance actually degraded over time from when we down selected to the vitreous material transformation material. So our response to the problem was to organize a technical interchange meeting, and we brought in subject matter experts from additive manufacturing, Regulus simulant properties, including the geochemical and geotechnical sides of simulants, high temperature ceramic material science people, and everybody spent the day just culling over a lot of the data between what happened at down select and what's happening now. Reviewed all the different stimulant changes and process modifications, and identified some really good recommendations for the ICON team to try out. So ICON is performing those experiments, definitely have the perseverance here. It is a schedule hit to our project right now, but we are working that out, and we do plan to have our Task 30 test coming up in September of this year, hopefully earlier than that. Also, one really cool thing is that we got to meet Leslie Stahl when the 60 Minutes team came out here to talk about impact with us and how we're working with ICON and all the cool things that we really do here, including testing in the V20 chambers, huge dirty thermal vacuum chamber that we got to test in. And it was 80 degrees when they were filming in the room. And it was humid that day. I think it had been raining, actually. So I apologize for my hair. It's what happens. But it was incredibly cool to meet a celebrity. And Leslie is an amazing person. She's been all over the world and has so many different stories. But it was really a pleasure. So kudos to the 60 Minutes team, and kudos to our communications team here at Marshall, actually, for doing that. Greatly appreciate it.
So as Jennifer mentioned, what you see on the left is what we at Marshall call V20, and it is a 20-foot diameter, 28 feet deep thermal vacuum chamber. And its mission in life is to recreate the thermal and the vacuum environment that experiments will see in space, so we can test them inside this chamber and gain confidence that when they go into space and they face this environment, they will function as they were designed to do so, or we catch the problems when we do the test in V20. Now, for this nuance, we have added a regular simulant bed. As Jennifer mentioned, that makes this a dirty thermal vacuum chamber so that we can actually perform the operations of scoop, tamp, filter, prepare the site, actually lay down a representative element of a landing pad that we're going to build this fall in Task 30. What this chamber gives us is a reasonably good simulation of the lunar vacuum. We can get 10 to the minus 7 versus the moon being 10 to the minus 13. We can match the lunar day and night temperatures. What we cannot match is Earth versus lunar gravity. But this gives us a lot of confidence if we test our system in there, that we know it's going to operate as best that we know how to make it operate once it gets to the surface of the moon. And like I said earlier, we will be testing all of those subsystems and all their functionality once we put those in the V20 chamber. Next chart. And you all have seen this in the beginning. This is our vision moving forward for impact. We want to be able to print landing pads on the surface of the moon. And as you can see there, we've done a lot of analysis on what that landing pad ought to look like. We're still taking a look because we're modifying the process. But in additive manufacturing, there's something called topology optimization, which maximizes the strength of the material where you need it maximized and minimizes the material where you don't need the strength. Can come up with some very unique and very strong designs. So there in the foreground, we're printing a lunar landing pad. As you can see a little bit further away in the center of the picture, we're printing a roadway, and we believe that would be the next series of infrastructure that would need to be constructed on the moon. And then in the upper left, you can see in the rear, and time-wise also, that's probably a later construction element that would be made, and that's constructing a habitat for astronauts to live and work in. So this is our vision for the moon, or it could be for Mars if the agency decides that we're going to Mars next. As we've talked about in this presentation, first we were going to the moon, then we were going to Mars, and now it's moon to Mars. So we're incorporating them all. And I believe that's our presentation. Are there any questions?
Thank you so much, Jennifer. Jennifer and Corky, thank you. All right. All right. Thank you, everyone. And now we are going to jump into the next part of the event, and we're going to start our school presentations. So first, we'll have Altoona Area Junior High School. Yay!
Good afternoon, everybody. And first and foremost, I would like to thank Rocco Scalzi and everybody at NASA for inviting us for an awesome opportunity to present our 2025 middle/high school research challenge. This is the Moon to Mars Blueprint for Success. Welcome to an in-depth study of NASA's Moon to Mars Planetary Autonomous Construction Technologies Impact Project. Learn how to apply Quarterbacks of Life Blueprint for Success to both NASA's lunar construction goals and your personal journey. We begin with the end in mind and beating the odds by attaining the unthinkable. This slide consists of 3 pictures, one of NASA's logo, our school district logo, and our high school football team. These pictures all symbolize success and teamwork. Here we have the research challenge overview and how we apply to our daily lives. First, we have to create a research team. Just like NASA, we have formed an effective team to tackle the challenges together. Secondly, we need to develop a presentation. We have created an informative presentation explaining the blueprint for success in life's ventures. Third, we have to apply impact. NASA uses success blueprint for lunar construction just as we do in our everyday life. Fourth, we need to connect personally. Even the smallest challenges require a mindset for success similar to that of ICON and NASA. We need to think outside the box. Here we have the impact project background. The challenge, NASA needs infrastructure on the moon for our Artemis missions. The solution, NASA's impact project partners with ICON and others to develop autonomous construction technologies. The leaders, led by geologist Jennifer Edmondson and principal Dr. Corky Clinton at Marshall Space Flight Center. Here's our blueprint for success, personal and impact application. 1, we have to define success. 2, identify stoppers. 3, set goals and dreams. 4, assess resources. 5, build our team. 6, make decisions and plans. And 7, stay positive.
All right, so here is Module 1 on success. So what is success? Success is a process of self-improvement that leads to forward movement in the direction of your dreams and goals. Success requires taking the right steps, learning new skills, and making deliberate choices towards your goals. So some success to us, students, versus success to NASA. For us, it could be getting a high grade on a test, winning a sports event, learning new knowledge, or becoming well-rounded individuals. For NASA, it could be placing life on the moon, stepping foot on Mars, exploring other planets, and learning more and more about space after each passing day. For both of us, it could be working well as a team, getting tasks done on time, and following directions given to achieve an accomplishment or goal.
So what is success to me? Success to me is all about improvement. Improvement is very important because even if you don't achieve what you're trying to achieve, you can always look back at your mistakes and learn from them. What success means to NASA? Success to NASA is a lot about improvement as well. Improvement to NASA can be so little because of how difficult the stuff that NASA is trying to achieve is. Even the littlest amount of improvement can go a very far way for NASA.
Up here's the definition of success we have. This slide here is the definition of success we have. It says basically that success is achieving the goals that you set for yourself and succeeding at what you like to do.
All right, going on with Module 1, we have Module 2, which is success stoppers. The definition of success stoppers are factors that impede progress towards goals. In addition, are personal stoppers. They are fears, anxiety, negative thinking, and another stopper is environmental stoppers, including resource limitations, safety issues, and natural disasters. Success stoppers are a problem for everyone, including NASA.
NASA has many success stoppers, including financial issues, lack of necessities, adapting to the moon, and transportation. NASA's financial issues include the cost to go to the moon. Each launch to get supplies to the moon would cost up to $4 billion, and NASA's total budget is around $20 billion. This shows how NASA is spending a minimum of 20% of their budget for only one launch. The lack of necessities. NASA has to acknowledge and make up for that is the moon doesn't contain any necessities such as water, food, or shelter. So when NASA goes to the moon and they are going to be forced to compete with the problem of taking supplies to the moon and Mars with the astronauts. NASA's astronauts have to adapt to the moon. The moon's gravity is only 16.6% as strong as Earth's, so it will take some time to adapt to. This causes some mental as well as physical challenges to the astronauts, as well as the intense training that they have to undergo before the trip to go to the moon. Transportation is also another struggle for NASA, for the plan is to 3D print houses on the moon, which means they have to move the 3D printers as well as the building supplies to the moon. And with all the extra weight, they can cause additional problems for NASA and its crew going to space.
There are many success stoppers that can stop us out of tuna, such as negative thinking, fear, and possibly finance. Negative thinking is caused by your peers or yourself and makes you think you're not good enough. This leads to you not even trying to achieve your goals. Fear is something everyone feels, but it must be controlled. You might have a fear of failure or embarrassment, and it's understandable, but it only leads to bad things. Finance. While as a town, we are very fortunate, there are people who aren't. Not having enough money will result in a lack of resources necessary to reach your goals.
Stepping stone 1 is dreams and goals.
Dreams are powerful creations of the mind that clarify what you want.
Goals are detailed, specific targets that ground dreams in reality.
Actions are steps that turn wishes into achievable outcomes.
I would say that NASA has dreams and goals of being able to successfully have humans on the moon and Mars that can do functional things like we do on Earth. Some of those things include having roads and buildings where people can drive and sleep.
As a student at Altoona Area Junior High, personally, one of my dreams in life is to make it to the New Balance Nationals for 100-meter hurdles. My goal is to train hard at every practice, cut off half a second, and give it my all at every meet that I have left.
After Stepping Stone 1 of the NASA Impact Project is Stepping Stone 2. Stepping Stone 2 is self-awareness, resources, and development. The first part of Stepping Stone 2 is self-awareness. This is understanding your own strengths, limitations, and personal success stoppers. This is also holding yourself accountable for your actions and asking for help when it's needed.
Next, number 2 is resources. Using resources is being able to identify the tools and skills available to you. The last part is number 3, development. Development is learning or acquiring what is needed for the task, but you don't have available. Now, let's hear a personal story.
Hello, my name is Abigail, and I'm an 8th grade honors student at AAJHS. Being in the honors program is both challenging and rewarding. It requires constant dedication, time management, and a growth mindset. One of the most valuable skills I've learned and developed is self-awareness, which is the ability to understand my strengths, resources, my progress along the way, and the areas where I can improve. Being an honor student is demanding, but with self-awareness and effective strategies, it is possible to thrive. And while NASA it might not be using self-awareness skills to write an essay or a book report, they do need them to launch rockets, float in zero gravity, and keep their cool when things get, well, out of this world.
So this correlates directly to NASA because they have to stay self-aware to the strengths and challenges that projects will face and to understand the difficulties that can come along with something even as basic as making sure that they have the correct resources.
Okay. Stepping stone 3, team support. Collaborative success. Achieving goals is a team effort involving people helping people. Enhanced clarity. Teams improve goal clarity and help identify potential success stoppers. Sustained optimism. Team support builds resilience when facing inevitable challenges. This is what team support means to impact success.
Impact needs team support from NASA and from their coworkers in order to get to the moon or Mars.
Without any team support, then everyone doing their own part of the project without any communication or support from the team members, then putting everyone's individual pieces together will never work.
Having team support behind you in a big project, like going to a planet or the moon, is essential to the overall success and safety of the project and people involved.
This is what team support means to us as junior high students.
Having a support group that helps a goal be completed.
Everyone doing equal amounts of work and
everyone's part being put together. People who get the job done on time.
People who encourage you even when times are hard.
As athletes on the Altoona track team, we know having team support from our coaches and teammates is vital to the success of our team as a whole.
I know that when I'm running and I see all my teammates on the sidelines cheering, it really gives me a boost of confidence.
When you have a support from a team, whether it's during a race or during a large project like going to the moon, you are more likely to succeed as a whole.
Stepping stone 4, planning and decision. This is a step where you take action to create your plans and make the decisions you need in order to achieve your goals. Both NASA and the AHS have many plans and decisions to make. First, let's start off with what is a decision.
What is a decision? Decision is a judgment or conclusion that can help determine what path to choose or what we do. Decisions are normal in day-to-day life, like when you pick which shoes to wear or what to eat.
What is a plan? Plans are intentional decisions that will help map out something that will happen. It's common for people to plan out buildings for even what you would do for next month.
Our decisions. We had to make various decisions in the making of these slides. Every student in the NASA program had to make a decision. We had to decide what groups we were in and who was presenting, who did what in the presentation, etc.
For us, planning was knowing what we were going to focus on each slide, when we would meet to discuss our process, and even what images we'd use on each slide. We had multiple plans fail, but we just restarted till we got one that succeeded.
NASA has to make even more important decisions than us. While it may seem that because they have such important decisions, they would be completely different, but they look fairly similar to ours, much like us, they have to decide who's going to work where and how they're going to go about that task.
NASA has many different things they have to plan too, like how to form a lunar base on the moon while also balancing their crew's safety. Much of planning should be centered around safety more than arrival, since they can replace any technology, but can't replace a person.
Stepping stone 4 is necessary to both our goals as students and NASA's goals to get a lunar base on the moon. With planning and decisions, we can both achieve our goals no matter how difficult.
Stepping stone 5, positive mental attitude. Having a positive mental attitude is a very important skill in everyday life. As a student in all of our endeavors, staying positive is very important, especially when life starts to get tough. Having a positive outlook on life can improve how you perform, whether it be in a sport, school, show, or etc. One way to stay positive and improve your attitude is having positive self-talk. Some examples of positive self-talk are saying, I am capable of achieving my goals, I trust the journey and believe in myself, I am worthy of love and respect, and I choose to let go of negative thoughts and embrace the positive.
Another way to stay positive is by setting goals and reaching to achieve them. Keeping a goal in mind can keep you motivated and determined. The next example of having a positive mental attitude could be accepting change and being open to it. Being open to change can be hard, but if you talk to yourself with a positive mindset, it will be a lot easier to go with the change.
One last way could be surrounding yourself with people who benefit you. Having positive people in your life who support you is something that can boost self-esteem and attitude. So, how can this relate to NASA, you may ask? For NASA, having a positive mental attitude is very important, because if they did not have a positive attitude, they would have probably never gotten to the moon. Another reason they need a positive mental attitude is because they are spending around 6 months in space. They need to stay positive because when you are positive, you will have much better health and work ethic.
Overall, you can see how having a positive mental attitude can help you thrive from young to old.
So in conclusion, we've learned several qualities. One quality we learned was teamwork, another was planning, dedication, positivity, and motivation. Going in a little more depth on these topics, teamwork played a big role in creating the presentation. Even though all of our groups work separately, we all combined to make this presentation. For NASA, teamwork involved hundreds of people working separately, but combined to make a bigger project for Artemis.
Next up is planning. Together with all the slides we had to make, there was definitely some planning. Deciding who got what role and how to divide the slides to present our research. Planning for NASA is creating blueprints for actual spacecraft and also deciding who worked on what side of this Artemis. Next is dedication. Dedication also played a pretty big role in creating this presentation because we had to stay locked in to make our presentation as good as possible. Dedication in regards to NASA involves never giving up, no matter how big the challenge.
Positive attitude helps us all create these slides. Whatever it was, working with people we didn't like or having compromise to create something. We all had to give up something and stay positive. To work through this presentation, NASA positivity in working environments, create ideas for improve and relationships to grow.
Our final message is that success is always an option, but you must make the effort to achieve it. In our own lives, we have learned that success means persevering through the challenging times that we face. An example of this would be during COVID-19. We had to adjust to learning online, which had a huge impact on our learning. We could have just gave up on school, but we got through it by not giving up. Doing this allowed us to become more successful students in the long run.
NASA can also relate to this. NASA should understand that success means not giving up what they believe in and persevering through their own tough challenges. For instance, they could give up because of financial problems or there is not enough community support, or they could continue pushing to make it through, to reach their goal. This overall shows that success means not giving up on what your goals are, even when it gets tough, because those challenges are a part of the journey that leads you to becoming successful. A big thank you from Altoona Area Junior High School. We are ever so grateful for this opportunity, and we show our appreciation by just doing what we can. Thank you.
Thank you so much, Altoona Area Junior High School. You guys did an amazing job. Thank you so much. All right, so we're going to move on to the next presentation. If I could have on the stage Antelope Valley Learning Academy, Learn for Life. Woo! It's just you all?
Oh, yes.
Awesome. Okay, well, when everyone gets here, I'll explain. So don't touch it. Okay. Okay. So when you're moving the slides, you're just going to press this button, and then this is the button to go back. The green one? Yeah, the green one is the one you want to press. Okay. All right. And you can adjust the mic for this reason.
There you go. What up, everyone? I am Deshaun, and I'm here today with my team, Nathan, Junior, Michaela, Trandy, Erica, Lorna, and Edward. And we are representing the Antelope Valley Learning Academy, class of Being the Odds. And together we researched NASA's Moon to Mars Planetary Autonomous Construction Technology Project. And first up, and we're going to show you how they use Being the Odds and Being the Odds with the stepping stones. First up, we have Nathan.
To NASA, success means more than finishing a mission. It's about reaching goals, keeping astronauts safe, and learning from every experience, especially the mistakes. Each mission helps them improve the next one, pushing the limits of space exploration and technology. Their idea of success is all about growing, discovering, and never giving up. What success means to me is reaching goals such as graduating on time. It also means to me is having good relationships that can support you when you're in doubt. Perseverance is also a big thing for me because it helps me stay focused and keeps pushing me forward even when things get tough. Next, you'll be hearing from Junior.
Success stoppers. The impact will face many potential success stoppers. One example is working under lunar environment. This is really dangerous because the moon has different temperatures during the day and night. During the daytime on the moon, which is called a lunar daytime, it can get really hot on the moon. The reason it becomes so hot is because the moon has no atmosphere, so it's exposed to the sun. Without an atmosphere, the moon wouldn't be able to contain the heat. When the sun sets, that's when it becomes lunar night on the moon. When it becomes lunar night on the moon, it gets extremely cold. It gets cold because the moon has no atmosphere, so when the sun sets, it doesn't stay hot no more. Which is why the moon has temperature changes. One of my success stoppers is lacking motivation. The reason that's a success stopper for me is because I've made mistakes before with school and with life, and bad thoughts could really stay in a person's head. When you're so used to being lazy and inactive, it becomes regular in your daily life. One day you'll feel motivated, But that little spark of motivation doesn't really last forever to a person that's used to being down on the daily. I'm going to learn how to overcome the success stopper no matter how much I struggle. I'm going to do whatever it takes to overcome that success stopper. Next up is Michaela.
Stepping Stone 1, Dreams and Goals. Impact's primary goals are to expand human knowledge through scientific discoveries and expanding presence into space and to the moon, and addressing national challenges, fostering economic growth. Their dream is to plan a long-time survival for humans on Mars. My dream is to complete my education and secure a fulfilling job. I aspire to achieve this goal not only for personal growth, but to continue a meaningful life for myself. The steps I have to take are to make sure I turn in 6 to 10 credits a month. My goal is to make people happy and help them with their lives and problems. I aim to spread joy and a lending hand to everyone as they navigate life's ups and downs. And up next, we have Trinity.
Stepping Stone 2 is self-awareness resources. Impact resources are a part of a bigger Moon to Mars project. It includes collaborations with a larger number of groups, all who play an important role in Impact's mission. When looking at Stepping Stone 2, I had to start with my goal, which is to graduate on time with my class. A weakness of mine is multitasking. I can overcome this weakness by being more organized and focusing more on what I am doing. One of my strengths is asking for help and giving help when asked by my peers. The resources that I utilize are my friends, family, teachers, and tutors. Next up is Erica.
Stepping Stone 3, Team Support. Impact is such a huge project that cannot be successfully done without a team. NASA has teamed up with private companies that help develop new technologies for space explorations. Currently, they have over 30 partners in 15 states that are providing critical support through various means, including conducting cutting space research, developing new technologies, and fostering a skilled STEAM workforce. My team support is my mom and my big sister. I am more than grateful to be in the same lifetime as them since they do a lot for me. Some of my friends are my team support since they are there for me when I need them most. My school and my teachers are my team support because they keep me doing my work so I can graduate. And now Lorna.
Hey, Bob, I think the thing is not working. Are you able to turn it on again? Ooh. Ooh. Okay, it's working now. All right, there you go.
Okay, thank you.
Is this the slide?
No. It's okay. Okay.
Stepping Stone 4, Decide and Plan. In order to achieve their goals, NASA has decided that they want to land the first woman and next man on the moon with the help of the Artemis missions. In planning this, they have to come up with a safe way to get them on the moon and have a way to communicate with them once they're up there. For my Decide and Plan, I decided that if I want to graduate on time, I need to turn in 8 credits a month. My plan is to go to a 4-year college. The reason for that is because of my mom. She's a big help talking to me, teaching me, and giving me a bigger image on college and my future. When I do go to college, I want to get my master's degree in veterinary science. The reason for that is growing up, being around animals and wanting to help them gave me the passion to one day want to work with them. And that passion has never gone away. And now you will hear from Edward.
Stepping stone 5 is positive mental attitude. To have a positive mental attitude, it means to be resilient and optimistic throughout life's challenges. To stay positive through projects like Impact, NASA has to train their astronauts through extensive physical, mental, technical, and teamworking training to ensure their readiness to any irregular living conditions up in space. On top of this, to keep a positive and stable mentality in space, they're given any resources needed to ensure their stability. For example, they're given access to a teleconference to speak with the psychologist whenever needed, and they're also strongly encouraged to journal and write to let out any frustration or even happiness that's experienced up in space. Doing these two things really helps them keep a good morale, positive, and motivated. As for me, I set a goal to graduate on time in May of this year, and I knew accomplishing it wouldn't be easy because I had over 130 high school credits to complete within 10 months. But through it, I built a positive mental attitude. Some strategies I've used to help me accomplish this goal was keeping myself reminded of the success and fulfillment that accomplishing it would bring me, focusing and prioritizing on gratitude and the happiness in my life, and positively journaling as well as reaffirming myself on both good and bad days. These strategies kept me moving forward and helped me accomplish my goal even when it felt as if all odds were against me. And to end our presentation, you'll hear from Deshaun.
In conclusion, these are Impact's 5 steps to success and how we use them with our dreams. And we would like to thank y'all for allowing us to be here to present. Thank you, NASA. Thank you, our teachers, for supporting us. Thank you for everybody that's here to support us. And thank you, Rocco, for supporting us too. And your team for showing us how to beat the odds. We appreciate y'all.
All right. Thank you so much, Antelope Valley Learning Academy, Learn for Life. You guys did a great job. Thank you. Next up, we have Antelope Valley Learning. Messed it up. For the third school, we have Hollidaysburg Area Junior High School. If you guys could join me up here. Just four of you? Just four of you? Okay, awesome. So this is the button to press to move to the next slide, and this is the button to go back, okay? And you can adjust this as you need, all right? Here you go.
Thank you for having us. This is a 2025 Hollidaysburg Area Junior High School Beating the Odds Project NASA presentation. Representing our school today is me, Swayam Patel, and our other presenters are Zach Blesha, Kendall Reed, and Ryan Grosser. Success. What success would look like for the MPACT program? Being able to improve our technology through the use of the scientific method in order to create infrastructure on the Moon and Mars. Develop, deliver, and demonstrate on-demand capabilities to protect astronauts and create infrastructure on the lunar surface. Some of our team's personal successes include Uriah getting second place in a chess tournament, me running a personal best 5K time of 2040, and Ethar placing top 15 in a math counts competition.
Success stoppers. Some of the success stoppers for the MPACT project are a lack of funding or resources, failed designs, technological limits, or time limitations. Some of the environmental success stoppers our group identified were weather, delays, and time. And some of the personal success stoppers were motivation, mistakes, and miscommunications.
The 5 stepping stones that we will talk about are dreams and goals, self-awareness, resource review and development, team support, decide and plan, and positive mental attitude. Stepping stone 1, dreams and goals. Here are some of the list of impact successes to date. Developed a specialized lunar pad, catching a debris, refueling or catching a rocket. Many, many more that we couldn't list on this slide. Here is some NASA dreams and goals for impact. Conservation of material, rocket reusability, ability to refuel rockets outside of Earth's atmosphere. Dreams and goals for the beating the odds project NASA. Some of our group goals are to have a successful day at Goddard Space Flight Center. Some of our personal dreams and goals are becoming animator and or making her own show. And their dream is to have a successful hockey career.
Stepping stone 2, self-awareness, resource review, and development. Goal awareness. NASA will need to perfect the process of creating materials to construct infrastructure on the lunar surface. Awareness of goal deficits, time, funding, technology, and morale. Self-awareness. NASA can operate with greater success when they receive ample funding for labor and technology. Resource review. NASA has scientists, astronauts, computers, rockets, and satellites. Resource development / acquisition. NASA will work with the private sector of the space industry to further develop their technology. Our goal is to have a successful day at Goddard Space Flight Center. Goal awareness. We need to create a presentation, attend group meetings, and have transportation to Goddard. Awareness of goal deficits, time, preparation, and limited resources. Self-awareness. We are more successful when we have all group members present and active during meetings. Resource review. We have teachers, technology, and our peers. Resource development / acquisition. Meeting with Mr. Scalzi, the Beating the Odds program, and acquiring a charter bus for transportation. These are some of our personal examples of Stepping Stone 2. On the left, one of our teammates wishes to have a successful hockey career. Sorry, the wrong side. On the left, one of our teammates says that he keeps his head up through the ups and downs and after a bad shift or bad game. And on the right, another one of our teammates says he needs to have a positive outlook on tennis even if he loses or wins games.
Stepping stone 3, team support. Some of MPAC's supports are that NASA provides technological resources and personnel. NASA contracts ICON to help create technology that will print 3D buildings, and that engineers collaborate to build hardware, develop processes for successful operations in extraterrestrial environments. And on the right side, you can see some of our personal supports. Stepping stone 4, decide and plan. NASA's decisions and plannings are to deliver and demonstrate on-demand capabilities to protect astronauts, create infrastructure on the lunar surface landing pads, habitats, shelters, roadways, berms, and blast shields using lunar regolith-based materials, and collaborate with ICON to help plan and prepare the construction of lunar infrastructure. And lastly, to work with NASA and privileged agencies to deliver payloads to the lunar surface. On this slide, you can see some of our own personal deciding and plannings. One of them is, one of our group members' goals is to have a steady hockey career using all their training and abilities. With a consistent workout and a good mindset, they will be able to achieve their goal and even exceed at it.
Stepping stone 5, positive mental attitude. Some ways that NASA needs to have a positive attitude are when working within the confines of the lunar surface, when funding and technology are unreliable, when not keeping up with timeline goals. When a task appears complex, NASA can reach out to private firms to collaboratively address issues at hand. Oh, I forgot to skip that. I went too far. These are 2 ways that our group members maintain a positive attitude while playing sports.
Conclusion. It takes hard work, persistence, and teamwork to achieve your dreams. Thank you all for listening.
Thank you so much, Hollidaysburg Area Junior High School. You guys did an awesome job. Number 4, we have Laurel Highlands Middle School. Awesome. All right, is this all of you?
Yes.
Awesome. Okay, you're gonna press this button to go to the next slide, and if you go too fast and need to go back, you press this button, okay? And then you can adjust this here. All right, I'll be right here if you need it. You want to click it one more time?
Okay.
Click it once so it starts in your presentation. Yeah, there you go.
Okay. Good afternoon. I'm Allison Fabry, and this is Laurel Highlands Middle School's slideshow on impact. I am here to talk about our personal successes as a team and the impact program's successes. This presentation will consist of 3 parts. Module 1 is about our successes and impact successes as well. Module 2 talks about success stoppers. And Module 3 is all about the 5 stepping stones for success. Some of the many personal successes of the team are making various sports teams, playing an instrument, getting into the National Junior Honor Society program, and keeping good grades. NASA's Moon to Mars Planetary Autonomous Construction Technologies, or impact program, has achieved several significant milestones in advancing autonomous construction capabilities for lunar and Martian missions. Here are some successes: developing construction technology, researching automated construction, and developing blueprints.
Hi, I'm Finnegan Barber, and I'm in 6th grade at Laurel Highlands Middle School. The impact program is about getting a spaceship from the moon to Mars. This, however, is a very difficult task. NASA needs to set up a kind of pit stop on the moon for the spaceship going to Mars. But NASA will have some problems or success stoppers that will keep them from reaching their goal. Challenges they will face are lack of funding, unfamiliar lunar materials, and repairing robots from Earth can make getting from the moon to Mars difficult, and finding talented people who can accomplish the task is hard. People can have a lack of ideas or can doubt their own strengths, and the known tools we are using aren't good enough for the mission. However, they are using prototype technology that is still being tested to complete their mission. We haven't been to the moon in over 50 years, so the terrain will be unfamiliar. Impact will persevere through their success stoppers and failures so that they can make it from the moon to Mars successfully and complete a mission that will change the way we travel through space. Sure, There will be obstacles, setbacks, and plenty of "are we there yet?" moments, but Mars isn't going to visit itself, and even though failure is there, we have to persevere to complete the mission. How does this slide thingy work? Okay, thank you.
Good afternoon. My name is Selena Matlock, and I am in 8th grade. While dreams are not goals, they clarify what you want in life. Goals are smaller successes that get you to where you want to go. For most of us, a dream of ours is to go to college. A dream for NASA is to be able to have a pit stop and a base to the moon so we can move from the moon to Mars and possibly other planets in our solar system. This is necessary for missions to the moon, Mars, and beyond. Stepping stone 2, self-awareness. If you know your strengths, limitations, and personal success stoppers, you are self-aware. Our strengths help us feel confident in our abilities to improve our weaknesses. To successfully 3D print landing pads and roads on the moon, it has to be with lasers to melt the regolith on the moon into a material that withstands high and low temperatures.
Good afternoon. My name is Tate Swaney, and I'm in 8th grade. The third stepping stone is team support. Team support is one of the many factors that help you succeed. It enhances the chance of success as a team. NASA receives support from a wide range of sources, including the U.S. government, private companies, international space agencies, and even citizen scientists to help its goals in space exploration and research. For us, our support comes from families, teachers, and even our friends. People who are successful understand that achieving their goals often requires the support, guidance, and direction of others. Stepping stone 4 is a process that helps you to grow in your decision making. There are many factors that go into decision making, such as discussions, remembering your progress, your mindset, and the outcome or effect of your actions. Deciding takes time. NASA has many things to decide, like what to bring on a space exploration, who to bring to space, and which way would be the best to get there. We have many things to decide in our lives as well, especially what we are going to do while we achieve our goals. Making decisions immediately can lead to problems in the future with your success. It is almost impossible to make the right choice without planning it first. NASA will have to decide and plan on certain ideas to make this a successful operation. These include blueprints of the laser that will melt the regolith and how to transport it. Without a plan, anything can happen and not necessarily a positive outcome. Stepping stone 5 is positive mental attitude. Everyone faces challenges in their lives, and this process helps us keep a good mindset if something gets in the way of our goals. Not all plans work out. Sometimes alternate routes need to be made in order to achieve our goals. Having a pessimistic attitude can lead to problems and the downfall of our success. By being mentally positive, it increases willpower to think and learn in order to send rockets into space and go to the moon and Mars.
My name's Arden Braun, and I'm in 6th grade. I would like to conclude our presentation by saying thank you. Thank you to the Goddard Space Flight Center and their team of educators and volunteers. This experience has been amazing. We have learned so much about space exploration and travel. Thank you for making today fun. Thank you to the Beating the Odds Foundation and the Quarterbacks of Life program. I hope that we go forward after today's activities and stewards of their mission. When you return to your schools, seek to lead, inspire, and motivate your fellow classmates to achieve success. Finally, thank you to our teachers. They've spent time getting this experience funded, and we, as students, appreciate their time and effort.
Awesome job. Thank you so much. And last, we have Muhlenberg School District. All right. You're going to press this button for the next slide, this big one, and then this one is to go back if you miss a slide, okay? Feel free to adjust this as you need.
Hello, everyone. I'm Leonardo Carbajal, a senior at Muhlenberg High School, and I will be starting off our presentation. So, Module 1 is success. And what exactly is success? Well, success is a process of self-improvement that pushes you towards your stated dream or goal. Now, a personal example for me is for science fair this year, I worked on a suit that aimed at countering atrophy in space. It would do this by using a series of elastic bands to help create a sense of resistance for your movements. However, this wasn't easy. I faced many adversities during this. Some are listed here. A main factor being, though, I haven't actually engineered anything up to this point. Some other factors is that I don't have much of an experience in research and development and public speaking. However, in the end, these challenges were bested, and I ended up placing second place in the engineering division in the science fair and winning a monetary reward. But what's important is just how this applies to impact. Well, if humanity wants a future in space, and we want to colonize the moon and Mars and have a future, there's going to be a lot of challenges. And the main important factor is just how we persevere through them and how we ultimately reach that success of settling space.
Hello, everyone. I'm Salem Davis, and I'll be doing the Module 2. The BTO definition shows both internal obstacles, like fear and doubt, and external obstacles, like your environment and time limits, matter. It helps us see what holds us back, and it reminds us that we face and overcome many different kinds of challenges. Relating back to Module 1, there were many success stoppers, like little experience in public speaking and inventing. Those are both internal success stoppers, and another one is balancing time with school and social life, which are external. These are common success stoppers with a lot of different projects. Time and limits make things hard, but we persevere. And working through obstacles, despite how hard it can be, helps us achieve our goals and our dreams. Even if projects are rushed or not the best, you can always come back and improve on it. Success stoppers cause difficulty in a lot of projects, and learning from these stoppers have made my personal success better as time passes and I grow.
So, just how could these success stoppers play a role in the impact program and NASA's future? Well, if we look into the past, we can see just how these stoppers will affect us in the future. Some past examples is with Apollo 13, an explosion of an oxygen tank, Skylab 1, with a failure of deploying solar panels, and even currently, NASA still faces success stoppers with the development of the SLS rocket and its significant delays, and even its capsule, Orion, that has experienced significant heat shield issues. However, the important factor is not about how many issues they face, but the fact that they pick their head up and they persevere through these issues. And that's an important lesson that NASA and ICON can learn, and this is exactly how they can address these success stoppers in the future. That future in space, it's going to be super hard to get. Failures are guaranteed, but the important factor is not just how many failures we have or just how catastrophic they are. What's important is that we pick our head back up and we come back stronger and we still move towards that goal.
Module 3 consists of our dreams and goals, self-awareness, resource review and development, team support, deciding and planning, and positive mental attitude. With the new discoveries about the conditions of Mars to the moon, we can create different solutions if they are different and to best survive on Mars. Dreams are powerful and often inspiring. They clarify what you want in life. And while dreams are not goals, they're important because they provide focus and desire. Goals ground dreams in reality. They give dreams their foundation by turning wants and wishes into reality. Our goals consist of becoming and developing skills of lifelong learners to continue our education into college and trade schools. Our dreams is to help others through medical practices such as prosthetics, surgery, and medicine. What is the role that Stepping Stone 1 Dreams and Goals have and continue to play in the Impact Project? NASA's goal is to land on the moon and Mars, and we will need ideas of how to get there. Dreams and goals, like being a surgeon and other careers include like engineering and architecture, have a major role in the Impact Project. Having these dreams and goals can give us motivation to continue with common goals. Our dreams and goals can help contribute to the creation of technology and are required to survive the conditions of Mars and keep the individuals sent there healthy and safe with sustainable housing and medical care.
I'm Bryson Smith, and I'm in ninth grade. Module 3, self-awareness. Each group has to have its members be self-aware in order to function correctly. Being self-aware allows us to assess our weaknesses and our strengths and play to them. To cover each other's weaknesses and strengths, we are able to be time efficient and diligent. Our overall goals can be accomplished in a timely fashion, and we can grow as individuals. There are two types of awareness: physical awareness and abstract awareness. Physical awareness is crucial when we are building infrastructure as plants, greenhouses, roads, structures. We need to be aware of our finances, of external things. And abstract awareness is important because we need to know what we are good at and what other people are good at so we can play to our strengths. Many people from our school are in band programs and sports, and it's a good example of playing to our strengths as each person plays their own instrument and knows their role in the band. Team support. Everyone has their own unique talents, as shown before. To balance that and support each other with trust and to work together. We all have a dynamic, and many clash. To be able to balance that and use the skills to create new ideas allows us to be more flexible. When we rely on each other to build strong team dynamics, we can support each other's weaknesses, which in turn ensures the mission success. With abundance of ideas and different people, we gain valuable knowledge from personal experience and network of academic allies.
I'm Layla Faust, and Stepping Stone 4, Decide and Plan, relates to us and our personal successes. Personal success stems from your endpoint, your dream. Plans are vital to get to dreams. Similar to a voyage to the moon, the endpoint is landing on a celestial body. However, the journey is the truly hard part because plans take time and are hard to follow. With Stepping Stone 4, we will be able to combine interest and personal dynamics to create a project that satisfies the whole group. Stepping Stone 4 also plays a huge role in the impact success with a variety of innovative minds creating both short and long-term plans to expand on our goals. We, along with others in the impact program, can create new solutions that others may not formulate alone. The Impact Project can demonstrate to the world that individuals with eclectic interests, knowledge, and backgrounds can work diligently to move humanity forward. Stepping Stone 5, Positive Mental Attitude, relates to us and our personal success. As individuals, having and keeping up with good mental health is key to our personal successes. Having a positive attitude can help with motivation and confidence in any scenario. It keeps everyone together to maintain equality. Stepping Stone 5 also has a key factor in the Impact Project. The Impact Project team needs to stay positive to build a collaborative and purpose-driven environment. This will help to foster a strong sense of belonging and motivation. Contributing to meaningful work with a team that values each member's input will ensure scientific success to get to the places we desire.
So, in conclusion, we at Muhlenberg High School want to give our thanks to NASA Goddard Space Flight Center, the Beating the Odds program, and the Blueprint for Success. Without all that, we wouldn't be able to bring these amazing students here. Also, thank you to Mr. Evans and Dr. Sirfas for bringing this amazing team of people together to give this presentation here at NASA Goddard. And yeah.